Now we're going to zoom in to a galaxy, and an interesting question you might ask is how likely is it that this very large number of stars, uh, something like 100 billion stars, how likely is it that they run into each other, that they collide? And we're going to use a very useful way of looking at this, which is the mean free path. And I'll write out what that means. It is basically the average distance that an object, in this case a star, will travel before colliding with another star. So this distance we write as L for the average distance, the mean free path, and it's 1 over n sigma. So n is a number density, and the number density for a typical galaxy, including our Milky Way, is about 1 star per parsec. So in other words, parsec cubed, where you have a cube and each side is a parsec. So we can write that out as per parsec cubed. And that makes sense if we look at our nearby neighborhood, where the closest star to the sun is Alpha Centauri, which is located about 1 parsec away. So our closest star seems to fit in with this, that we have our own cube of 1 parsec cubed for 1 star. All right, now the sigma here is what's known as a cross section, and this quantifies the likelihood of the collision. And here we're going to look purely at a geometrical case where you can think of 1 star that is traveling into the screen, and what does it see head on? Well, it sees another star, and if you have the projection, you can make that a flat 2D circle, which is shown on the bottom here in the diagram. And for them to collide, the furthest apart they can be is when they're just barely touching on their edges, and they each have a radius of r. We're simplifying, they have the same radius. So this dashed line then is the total area where they would just barely collide. And this cross-section area we're going to call sigma, and this is the geometrical one. And so this area of the dashed circle is pi times 2r squared. All right, so we can plug that in, and if we do, we get some average distance that the star can travel. But the galaxy is very large, so what we would probably like to do, in fact, is to think about what would the time be between collisions. Because if this is a very long time that it takes, on average, for 1 star to collide with another, then you can compare that to the age of the galaxy, and if it's on the order of the entire age of the galaxy, then we know that it's pretty unlikely. And if it's much longer, then it's very unlikely. There's just not enough time that these stars will collide. So we can write out that the time between collisions, tau, and here I'm going to use a subscript geo because we're going to say that this is related to the mean free path, and this is divided by a velocity, but we're going to substitute in that now we're using this mean free path is using the geometrical cross-section, and we are also have to include the velocity. And this makes sense from dimensional analysis, that you have a length divided by a velocity gives you time. And this velocity, notice the subscript ran, which is saying that this is the random velocity. We've already seen that stars, including the sun, are in an orbital, a circular path around a galaxy. And if you could imagine that that was the only motion, then these stars would actually never collide. They could just continue rotating around and be relatively fixed next to each other. But there is also some random velocity where you are not in the purely orbital motion, but you also have some other component. And so that random velocity component is smaller. It's about 20 kilometers per second. And you remember that the orbital velocity we just said was something more like 240 kilometers per second. So it's quite a bit smaller, about a factor of 10 smaller velocity that you get at a more random direction, which would then make it likely that these stars could collide. So if you plug in all of these values, including the typical radius of a star, you get a pretty large time. So this is on the order of a billion years. Whereas the age of the galaxy, we were saying, was something like 10 billion years. So you're a factor of 10 to the 8 larger in time. And actually, the entire age of the universe isn't much more than 10 billion years on this scale. It's on the same order of magnitude. So we're talking a much longer time than the entire age of the universe. And so this is extremely unlikely. However, you've hopefully noticed that we made a huge simplification in our cross-section. We were saying that this is just assuming that these galaxies, these stars inside of the galaxy are moving like balls that are not attracted to each other, that are just freely moving. But that is not true. There's the gravitational attraction, which will want to pull the stars towards each other. And so if we now consider that here, we have a diagram on the bottom where we have a star that's moving from the left to the right, shown as a straight line, and just geometrically it should miss the star that's shown above as the yellow circle, but it will actually collide because it's close enough, just barely close enough, that the gravitational pull between the two stars causes it to change its direction and then fall into the other